All right, so today we're going to be starting piecewise functions. Okay? Piecewise defined functions, and it's exactly what you think it is. It's literally a function made up of pieces of other functions. Okay? So for this one here, we have three functions there. Now yours is not color, so if you want to with the actual colors, if you want to color them that color so you know what we're dealing with. All right, so we have three different pieces to this function. Now, that's the first thing that's a misconception. Piecewise functions are one whole function. Okay? So if you notice, this has right here f of x, right here. F of x is defined, a piece of it by a linear equation, a quadratic, and a cubic. Okay? And that's why for this function, we see all three pieces. We see part of a linear function, we see part of a quadratic, and part of a cubic. Okay? But this is one function. And we are still dealing with functions, which means it still has to pass our vertical line test. Okay? If it doesn't, then we did something wrong, because by definition, it's a piecewise function, and functions pass our vertical line test. Okay? Any questions so far? No? All right, so let's talk about the easiest way to look at it. Piecewise functions are basically divided up into sectors or quadrants, okay, based on our domains. So the second part of a piecewise function is right here, where we've actually divided up our domain. So if you look, our linear function here only shows up when x is between -5 and -2. And when we come over here, we can see right here from -5 to -2, that's where we see our linear piece. Then here, the quadratic is in between -2 and +2. So here to here, -2 to +2. And the cubic is from +2 to 4. So from here to here. Okay. Now, to make things easier, what I always teach my students to do is when they're dealing with a piecewise function, those what we call breaks in our domain. See how our domain breaks, our x values break at -2 and +2? I always tell my students to draw kind of like asymptotes, like a vertical asymptote to help you out. So for instance, and I generally use yellow for this, I'm going to make a dotted line. So right here at -5, where my domain starts, and then it ends right here at -2, and then +2, and then at +4. So what these basically are to symbolize where our functions are going to show up. The linear piece, the quadratic piece, and the cubic piece. Okay? Now, just like any other function, we also have inputs and outputs. So that's what we're going to deal with first. So if you look right here, it asks us, what is f at -4? Okay? So this means that we're going to plug into our function -4, right? There's one tiny teensy-weensy problem, right? Which of these equations am I going to plug it into? Do I plug it into the linear piece? Do I plug it into the quadratic? Or do I plug it into the cubic? And how do you know which one to do? The first one? Why do you know it's the first one? Yeah, remember, this is my input, right? That's my domain. So I got to check to see, is -4 in the domain of my linear piece? This one, or this one? Well, -4 is in between -5 and -2, so that's where we're going to plug it in. And I should see you literally minus -4 minus 5, like that. So I can see visually here which one you're plugging it into, because this is the linear piece. So we plug it in, -4, that's +4, +4 minus 5 is -1. Okay? We're going to do the same thing for -2. So which part am I going to plug -2 in? The linear, the quadratic, or the cubic? So this one's a little trickier because -2 is in both of these, right? But look, for the quadratic, this is right here only when x is greater than -2. It's the linear function when it's equal to -2. So you need to be careful there. Okay, so again, you're using whichever domain you need to use based on the number, but sometimes it lands on that number, and then you got to look at your symbols. So yes, I'm using the linear again. So this is -2 minus 5, which will give me +2 minus 5, which is -3. Now we do +2. So which piece, linear, quadratic, or cubic, are we plugging +2 in? And again, we look for the symbol because 2 is where my domain breaks. So which one is equal to 2? That would be my cubic. So we got to plug it into the cubic. So 2 minus 3 cubed plus 2, which gives me -1 cubed, which is -1. -1 plus 2 is 1. And then the last one is 0. So which one do we plug 0 into? Linear, quadratic, or cubic? Quadratic, because 0 is in between -2 and +2. So we get -0 squared plus 1, which is 1. Now, that's if we have to plug it in that way. Of course, we could have found all of those same values by doing what? Looking at the graph. Now, there's one thing that my graph doesn't show me that I need to show you guys. So right here at -2, like when we had this issue, did we plug it into the linear or the quadratic, right? Here, the formulas told me that I was definitely going to plug it into my linear equation, right? But if I was looking at the graph, especially yours that doesn't have color on it, would I be able to tell which one I plug it into or where it was? There should be an open circle right here, like this. The red one is actually, the red graph has an open circle there, and then the linear function actually fills in that circle. That's why you don't see it there. But you should definitely draw the red one there as an open circle. What's up? Okay, so let's talk about the domain and range. So on piecewise functions, there's a way to do domain and range, and it's called projection. Okay, where you literally project the function onto the x-axis or onto the y-axis. Okay, that's a fancy way that, like, the way that most of my students get to remember it is I'm basically going to smush my function onto the x and onto the y. So I'll show you what I'm talking about. So let's start with the range, okay, because it's easier to show. So I start with my linear function. So my linear function goes from here to here, right? So imagine if I took this part of the linear function and started to smush it, like literally just start pushing it towards the y-axis. This point right here is going to get smushed to right here. And this point right here is going to get smushed to right there. And then it covers all of these values, right? We're going to do the same thing with the red one. The red one, this is going to get smushed right to here. This one's going to get smushed right to there. And then it's going to use all of these values. So you see how I kind of just collapsed it on the y-axis? And now we're going to do the same thing with the blue one. And we're going to take this point, and it's going to get smushed to here. And this point's going to get smushed to here. And then it's connected all the way from here to here. That shows me my range. And this is what we typically do with range. So my range starts right here at -3. And see how every point is covered all the way up till +3. So what's my range? From -3 to +3. Are they all included? Yeah. So my range is from -3 to +3. Sometimes you can just do the lowest and the highest point, but what if this had a break? What if the cubic didn't start at 1, it started at 2? There would be a break. There'd be a hole in there. So you'd have to do 2 pieces of the range. Okay? So now we're going to do the same thing with the domain. So we're going to take the black one again, but this time we're going to smush it onto my x-axis. And so this point goes up to here. That's already there. So this one is here. And then the red one starts here like this, smush there. This one goes here, and everything in between there. And then the blue one, this starts here, ends there, and everything in between. And so again, our domain here is going to be from -5 to +4. And again, we lucked out because these filled in. So we have no gaps. So basically, our domain is from -5 to +4, all of the values. Okay? And that's the easiest and fastest way to do domain and range. Now, also, our equation right here has the domain. This is my domain. So as long as there's no breaks here, you can just use these values. So see how it goes from -5 to -2, and then from -2 to 2, and then 2 to 4. So basically our domain is from -5 to 4. Okay. Now, if you have the equation, you can do that. If you have just the graph, you'll have to do it projection style. So that's my domain. From -5 to +4. And of course, since they're included, we use brackets. Now, we'll get to maximums and minimums in a minute. Let's deal with our x-intercepts. Okay. Now, again, x-intercepts, we can have anywhere from 0 to an infinite amount of x-intercepts, okay, depending on our function. Now, graphically, this is going to be really easy because we can see them. So I'm going to erase all this so it makes it easier to look at. Okay. So here we go. Our x-intercepts is basically where our function hits the x-axis. We have 3 x-intercepts. We have one here, there, there, and there. So those are x-intercepts. So at -5, 0, at -1, 0, and at 1, 0. You should only have one y-intercept, because if not, we're not dealing with a function. And our y-intercept is right here at 0, 1. So y-intercept is at 0, 1. Okay. Now, if you don't have the graph, again, it becomes a little more problematic. I didn't have to go and find the x-intercept for each one of these functions. But then I'd also have to test it against my domain and make sure that that x value is in its domain. For instance, if we did that with the cubic does have an x-intercept, but it is not between 2 and 4. Okay, it's actually in the domain of our quadratic, so we couldn't include it. All right, so this is going to be one of those things, especially in Algebra 2, that they taught you to actually go back and check your answers to make sure they make sense. Okay, which is a lot of what we're going to be doing this year. Can you tell me why it makes sense? All right, so let's talk about increasing, decreasing, and constant. Okay, the last part, and then we'll go back to maximums and minimums. So, increasing, of where a function is increasing. The easiest way to explain increasing and decreasing and constant, in physics they talk about, or in science they talk about slope. And if the slope is positive, your function is increasing. If the slope is negative, your function is decreasing. If your function, the slope is 0, it's constant. But basically, the easiest way is, are your y values getting bigger, or your y values getting smaller, or your y values staying the same? That's the easiest way to think about it. Okay? So look at this linear piece. From here, from -5 to -2, my function is going down. The y values are getting smaller. So this is decreasing. Right here, decreasing. Then right here at -2, it changes, and my function starts increasing. So right here, it is increasing. Till I get to this point right here, that maximum point, my quadratic, and then from here to 2, it is decreasing again. And then from 2 to 4, it is increasing. Okay? Now, again, I'm being overly simplistic of the whole idea, but that's basically the way you find out where a function is increasing and decreasing. Are the y values getting bigger or going up, or are they getting smaller going down? Okay? And then you just write it. So the function's decreasing. You got to write it as a interval. So from -5 to -2, and notice I'm not using brackets, and from 0 to 2. So that's where my function is decreasing, from -5 to -2 and 0 to 2. My function is increasing from -2 to 0 and from 2 to 4. Okay? Real easy. This function doesn't have any places where the function is constant. You would literally need a constant function for that, a horizontal line, to see where that happens. Okay? All right. So the last part we're going to talk about today are maximums and minimums. But to do that, we got to talk about there's two different types of maximums and minimums. Okay? So for maximums, I'll do this in purple. For maximums, we can talk about what we call absolute versus relative maximums. And this is going to be important, okay? And I really need you guys to pay attention. When we talk about, especially when we get to calculus, we're going to talk about this a whole lot more. But relative maximums or minimums mean in an area, like a small area. Absolute means throughout the entire thing, okay? So for instance, if I go up to my graph, okay, and I'll get rid of all this increasing, decreasing stuff real quick. So if I'm looking, okay, will you agree with me, this point right here is a maximum. It's a maximum for my quadratic, right? But is it the absolute maximum? No. Where is the absolute maximum? Right here. This is my absolute maximum. It is the highest y value my function gets to. That is my absolute maximum. This one is what we call a relative maximum. And this one here is also a relative maximum. Okay? Now, here's the confusing part. An absolute maximum can't be an absolute maximum unless it's first a relative maximum. Okay? It first has to be a relative maximum before it can be the absolute maximum. For instance, you can't be state champions if you're not first district champions. Because if you can't even win the district, there's no way you're going to win state. And obviously, if you're state champions, then you had to have won your district. So in this little area, you are champions, but also champions of everything. So you see that makes sense? So before you can be an absolute maximum, it has to be first a relative. So we often find all of our relatives first, and then we decide which one is the absolute of those. Same thing with minimums. So if I'm finding minimums, this right here is a relative minimum. This right here is a relative minimum. But which one is my absolute minimum? Just this one. This one is also my absolute minimum. There's no minimum here. This is not a minimum. Because it's an open circle, you cannot classify that as a minimum. I think I just hung up on them. Okay? Any questions?